how would a smart high school student put this on a computer? I say high school because it really requires nothing than Euclidean geometry. And sweeter still, we'll be able to write analytic formulas for Jacobians, and they'll be very intuitive. So there's one system in which, and we'll be even able to compute stability of periodic orbits analytically for a few orbits. And I'm actually very proud of this because I had a collaborator that produced 1,000 orbits, and I analytically computed the third one, and he was wrong at 1% level. Now, in this class, we expect you to be good to machine precision. This is deterministic chaos. So he had to shave his head in shame. No, he didn't, because the modern German has no pride, but he fixed his program and everything worked. So, it's wonderful to have kind of analytic thing at hand when you can have it. Unfortunately, it's so rare, but this is one case we can do it. So let me now draw a picture. We used to show overhead transparency. We don't do this anymore, but it's much more beautiful than what I'll draw. So here I'll draw. We'll specialize now on the following problems. We'll put few disks in a plane, and we'll be so lazy we'll only use 3. If you use infinitely many, that's called Lorentz gas, and it's a very useful thing in statistical mechanics. If it's 3, it's just, when you have a pinball machine and you send balls from here, then at the top there are 3 disks, and they're doing chaos for you, randomizing on dynamics. And in the movie I'll put beautiful paintings of these pinball machines. If you don't believe me, that's what they look like. And we'll take very small point, infinitesimal. Turns out it's not crucial, but the only thing that matters is a circular elastic scattering, and it cannot gain angular momentum. So the only energy is just in the motion. And we'll get started someplace. And what this thing will do is, like in any pinball game, it'll bounce maybe a few times. If I'm very good, then it'll fall apart. It'll fly out. And I'll use this to explain everything about how you think about chaotic dynamics. So this is a typical pinball game. Now, if you're a very good player, you might aim it in such a way it bounces a few more times. But it pretty soon turns out that if you want to control 10 bounces in the future, you have to have your initial condition specified to 1 Fermi or something, to subnuclear distances. So it's not going to work unless you cheat. That's called control theory. You can do this. As the pinball wizards do, they actually move the table. We're not allowed to cheat. What I want to describe now is how I depart from here and how I depart from the next disk. And that is kind of very elementary geometry. So here am I on one disk. And then, so in early Renaissance Italy, there was a competition for who will paint the Duomo in Florence, the cathedral. And competitors came with beautiful pictures of Madonna, etc. But Giotto, he came and he drew a circle by freehand for the jury, and they picked him, and they did very well. Now I'm not Giotto, but here we are. This is a circle. This disk is impenetrable, has a reflecting circular wall. I'm doing this to test the video system and also Kimberly's auditory. So I shoot out, and I do this at a position S minus 1. Time and S minus, I'm here on the perimeter. This is S. And I do this with uniform velocity. A vector, in our world, it's a unit vector. What it does, reflects here, and to see how it reflects, I have to write the line that connects the center of the disk at time n. That's a symmetry line. And the specularly at the same angle, and that's Vn plus 1. And it hits the disk at the point. So now I want to explain how you compute this position and this velocity if you're given your starting point and the center of the next disk. So usually the billiard is described, you just specify coordinates of the disk and their radii, and that's how you specify the billiard, the pinball kind of billiard, like this one. The beauty of this simple problem is this is specified, a line is a linear problem and a circle is quadratic problem. And it turns out to evaluate this point, we'll only have to take square root once, and that's all. Everything is elementary. You don't even have to compute the sine or cosine or anything, with trigonometric functions. And if you look at competing books, they're fulls and sines of cosines, etc. So they never tell you that you don't act. And if I know where I know where the center of next vector, I'll call it D. Now, what I also know is, I know the vector that's normal to this line. And this vector has a name that you must have seen. It's called impact parameter. So in scattering problems in electromagnetism and quantum mechanics, this tells you how big the scatterer is. Usually it's some potential, but here is a very literal quantity. The disk has a radius, and if your line goes outside, you don't see there is a disk. And if the line is closer than impact parameter, and there is the radius of the disk, I'll call this A, and the disk is defined, a point on the disk, for example, this point here. So now, in four-dimensional phase space, this is a two-dimensional configuration vector n minus 1. In our Poincaré section, it's specified by S n minus 1. And this is, let me just write the next point in 4 dimensions. So what is this has to satisfy? It has to satisfy that x n minus the center of the nth disk, because I'll continue doing this, squared is the radius of the disk square. So first thing we have to figure out, am I going to hit the disk? To do this, I can construct, I'll rotate m at the velocity at n minus 1 by 90 degrees. And I'll construct a vector u, and 90 degrees in a plane is very simple. You just exchange x and y. So construct a thing that has components v minus 2. So this is by construction normal to that. Then I can compute the parameter distance as Bn equals so the distance along here as a product of this thing times u n minus 1. This by construction is a unit vector because v was a unit vector. So that gives me this distance. Now, everything I write might be wrong, right? So I expect you to keep me honest. So collision happens if, and this is right angle, so I can define this thing here. Collision happens if c square, which is the difference of the radius minus parameter, or you can say that, or you require that b n over a n is smaller than equal than 1. So when you write your program, what do? You write a routine which computes the intersection of this line and the circle. They'll require some kind of quadratic equation. And then you check whether b computed, from the information that you already have. You know the distance to the center and next center, and you know this 90-degree rotated velocity. You just have to check whether it's smaller or equal to 1. If it's smaller to 1, you have a collision, so you continue. If it's larger than 1, you don't have a collision, so you keep checking whether your line is intersecting any of the other disks. If you have only 3 disks in the plane, you have to check only 2 disks. And if it doesn't intersect either one, then it's run off the table. You'll never come back. So it's very quick as a computation. It's as simple as it gets. So now the next step is, okay, we hit the disk. What do we do then? I find out that b is smaller than 0. I'm hitting the disk. Then I have to compute, the time of flight, because in dynamics I care about when will I arrive. So time of flight, because velocity is 1, is same as the length, and so I'll call it time of flight between n minus 1 and n collision. And I don't know whether to put minus 1 or not here. Maybe I should put minus 1 here. And what's time of flight? Well, that's very easy. That's this thing here minus Cn, which we already computed. So time of flight is Tn dn minus 1. Now you multiply it by velocity, not by turnaround velocity. That gives me this whole length. Minus c of n. And c of n is the positive root of a square minus b square n. So this is the only difficult operation, only nonlinear thing. So to find time of flight, you need the root. And you might wonder, what is the minus sign? In some cases, like in quantum mechanics, you might actually care about minus sign. Minus sign tells you what the far away intersection is. So the line intersects twice, but you care about the first intersection, and that's why it has a sign. So that's a time of flight. And then that tells me I have started here, I ended there. Now I have to find out the momentum. So this gave me the position, but I need the momentum. And so reflection is, we have this axis, this an vector. So the unit vector pointing out here, because I need this unit vector in my formula, so I need n here, normal to the circle right there. It points radially, so it's very easy. And I just write it down. It's 1 over an to make it unit, radius of the disk. And then it's b and u, and this is the impact parameter that we computed, minus cn, and I'm putting this hats, well, okay, the unit vectors, both of them, vn minus 1. So that's the formula, check it yourself, for which way this guy points. And then the reflection is, so let me call this calculation, I'll call it shift S. So that's what happens while momentum is not changing. So I'm just drifting in the space at constant velocity. And now I use my specular law to describe the reflection. What happens at the reflection is I can define the end point of this to be, x prime. But in reflection, the position doesn't change, so that's the same. See, what didn't change here is the velocity didn't change. So we're just moving in space. I get xn, and I get instantaneous acceleration. So I get a delta function acceleration that, because this is an infinite wall, which in instant in time changes my momentum by the specular law of reflection. And because it's a mirror, you get a minus sign here, plus 2. If you hit it directly, you just come back. So that's this minus sign. And but you have to now also take care of the wall normal component. So that's it. So you write a little routine, exactly what I did here. And what it does is it gives you the next point in your full phase space coordinate and next velocity in full phase space coordinates. Now, if you want to go back to our Poincaré section, then there is actually a little unpleasantness. I disagree with myself. There is nothing unpleasant. So what S is some arbitrary coordinate, because you have to set z equals how you move around the parameter. So it's the same as the angle, the S is, and that is unpleasant. So to compute S, you have to take arc sine B. So X is, so that's, that's actual real thing. That's worse than a square root. And this one because you know the p parallel. So you can code this and you'll immediately get million bounces, on your iPhone or whatever your supercomputer is. And the dynamics is now split in two parts. The free flight part, followed by reflection, and that's associated with, at time n, there's a transformation that puts me from here to there, which is a linear operation really. The S is, it's computable the way I told you. So this is my map in the full space. F one-time map going from four-dimensional coordinates. This is where you end up if you started. I don't feel like decorating this with letters. Okay. So four-dimensional vector n plus 1 from four-dimensional vector xn. And at the same time, you have the dynamics in the Poincaré map because you know exactly where you are at every iteration. and what the parallel velocity is. So all it requires is you go forward, you see where it intersect the circle, you compute the intersection, and then you reflect your line along this line, and you keep going. And you need one square root because circle is quadratic curve. Now, if you have a general billiard that I gave you before, it might be actually numerical calculation because if there's some, epicycle specifying what your circle is, it might require more than just a square root, almost certainly. So that's the number one about billiards. And the second thing about billiards that's very sweet is that not only dynamics is trivial, tuk, 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 but stability is trivial. And I credit Sinai and Bunimovic for writing it in a very elegant way. It's so elegant that I won't do it here. But it's, one step what I do. I'll put it, it's right now, I think it's in a chapter or maybe only in the private version of the chapter, but I'll put it in appendix. So, they write some beautiful formula in terms of continued fractions. And that's very important for them because they use it in proving ergodicity and stuff like that. But here is the smart way to think about stability. As I leave a wall of the billiard and I move on in the world, so I start here and I move in a two-dimensional plane, four-dimensional phase space. This is a little misleading. Let's do it this way. I want to emphasize that there are coordinates that we use. We are using x1 and x2 coordinates. But the Dr. Strangelove coordinates are the smart ones, the co-moving ones. As I move here, what kind of perturbations can I do to trajectory if there are small perturbations? One is I can just shift the trajectory orthogonal to it, because if I move along the trajectory, nothing interesting happens. So the only orthogonal dimension is important. So I can define a local coordinate. I'll call it dz. So it's a 90-degree at the motion of my particle. So that's a transformation in position space. Now the momentum, what is momentum? We wrote our position in 4 dimensions as, Q1. I'll try to fix it up. These are 4 coordinates, but we happen to know that P magnitude is 1 in our convention. And so this is a unit vector, so the only thing that defines this vector is its angle in my coordinate frame. So there's some angle here, theta, in my local coordinates, my own coordinates. So the way to really write this is to say that this is Q1, Q2, sine of this angle, cosine of this angle. So momentum has to do with angle. The only change of the momentum has to be angular change because its magnitude cannot change. So the other natural coordinate to use is as I move on my trajectory and perturb it is to change the angle. So that's an acceleration, change of the momentum, delta theta. So acceleration, and this is translation. So now let's see what happens to the particle. As long as particle is moving freely, there are no accelerations on it. So the only thing we can study is how it moves transversely. The moment it experiences a potential, here potential is 0, here potential is infinity, then there is no translation. Everything happens instantaneously in space, but there is a large acceleration because momentum gets shifted by a finite amount. So let's just do first the free flight and study what happens to small perturbations. That'll give us the Jacobians. So free flight. We do perturbation, okay, the Hamilton equations for this particle. I'll allow myself to use the word because you have seen mechanics. So. Are that time change of q is and time change of momentum, acceleration is minus So in free flight, Hamilton equations are very simple. dz, this transverse coordinate, is just proportional to the momentum change. Why is that? Because if I decide to move at an angle to this line, my distance from the line will be changing proportional to the time. And dt of the momentum, d phi, is 0 because there is no acceleration. So this I can integrate, and I get a formula from going from here to there in the free flight. I get that dz n minus 1 of x. So what I mean by this, I had some transverse displacement along this direction. And by the time I hit the disk, or infinitesimally before I hit the disk, I've flown this length, which I know how to compute. And the growth of the distance is just proportional to the time. But there are no accelerations, so the momentum doesn't change. So this is a situation, infinitesimally in time before I actually hit the disk. Now, infinitesimally after I've hit the disk, which will be pluses rather than minuses, I'm going in a totally different way. So now the Jacobian, this is a linear equation, And Jacobian associated with the translation, I really have to get all the letters right. This gives me a Jacobian with a free flight, which is 1, 1, 0. So this is the deformation of the neighborhood in a free flight. Jacobian is just derivatives of this, partial derivatives, and this gives me 1. This gives me 1. Doesn't depend on z, so I get 0. And here I just get the time of flight. So here is an analytic formula for Jacobian. And we already know it because the only thing we have to compute is this distance between the two disks, and we did this. Are you okay? All I'm saying is, if I'm going at a little angle, time till later, the distance will be proportional to the flight because we're just separating it uniformly. But that says Jacobian is extremely simple. So now what happens at reflection, you can think of it like what would happen if I shine flashlight on the edge of this disk. So what happens is that if I'm coming in here and my neighbor is coming, delta z transformed and maybe minus delta z, just to make it look like. What will happen is this one will deflect like that, that one will deflect like that. So because I'm looking at the mirror, which is convex, I suppose, so do you know how to remember concave versus concave? Never mind. What will happen, it'll spread out. Now, what it cares about is this footprint here. So if I hit it straight on, delta z will not change. And if I hit it at any other angle, it won't change either, right? Because nothing happens in the distance. The only change is in angle, which is acceleration. If I hit it very close to this grazing point, then I'll have a huge effect. You know, the thing that is grazed goes straight, but the one that's here goes at a big angle. So what I really care about is the angle theta. So let me write it. So remember, this is my impact angle here. And this thing that my dz is reflecting from of the order dz before the reflection minus all interval dz over cosine. So when theta is here, so bouncing exactly back, theta is pi, this is 1, and the interval is the same as dz, but as I approach the edge, this gets very stretched out by this cosine theta. So that's what this interval becomes. And now I don't have a quick way to explain the angles, so that I hope you will draw at home and maybe give me a nice drawing how to explain the angle. But if you were moving here is a delta theta angle. Delta theta angle before. If this is a flat plane, this delta theta will not change because everybody is going to reflect the same angle. If it's a very small thing, it's changed hugely because a nearby trajectory will spread out. So it really cares about this curvature. And the formula is true for anything that locally can be thought of. Circles have local curvature, so we'll call this rho of n. And what happens at this instant is that this distance doesn't change. This is instantaneous. So But there is a reflection, because if I was going here and I go out, what was my right now becomes my left. So there's a minus sign here. And so nothing happens, but I experience an acceleration. So delta theta after the acceleration, again, it's minus delta theta before. This comes from reflection, but now you get a term which is minus 2 over rho n cosine. I can't explain 2 here, but 1 over rho must be here, because the smaller the disk, the more defocusing it is. And cosine of the impact angle must be here, because the more to the grazing I go, the smaller this angle should be, and the more spreading, more acceleration I should get. And now that written as Jacobian gives me Jacobian for one iteration in reflection, which is 1, 1, because these two guys are there. But now I pick up, and there is a minus, minus, so there is a minus in front of the whole thing. And I pick up thing I'll call it reflection coefficient Rn, but Rn is this quantity. So just by looking at the co-moving frame, we get extremely simple and very intuitive formula of what the dynamics is. It tells me that if I start someplace on a billiard, I start on it with some velocity and some position. The first algorithm told me how I compute the next velocity, but in the co-moving frame of it, I also just get a Jacobian. So Jacobian for one iteration. So what happens if I perturb transversely or angularly around this trajectory? The Jacobian for one iteration is a first fly freely time t, and this is just a matrix, and then I reflect. And so the first algorithm told you how to compute it. Once you compute it, you know all the numbers, because you know all these angles, radii, and time flights. So you know the Jacobians. So once you compute the orbit, you know its stability. It's just simple, no extra computation, you just substitute in this. So for example, I'll give you at some point problem sets in which, suppose you have two disks and you're trying to play a very good pinball game by bouncing around these two disks. You go this way and that way. So mathematically you can do it. If it's on a line connecting the centers, this will always go forever. But you can now analytically compute its stability. So you can compute that Jacobian of this prime orbit is thing that cares about the flight time. So this part is having to do with accelerations and potentials, and this one has to do with free motion. And Jacobian is just product of those things. Now, you can immediately check the determinant of Jacobian is determinant of these two guys. But when you look at them, they have 1 on diagonal, 0 here, so this is 1. And because there is a reflection, there's actually -1. But basically, the volume is being preserved, phase space volume. So that's something from mechanics, comes out straight. And again, I'm running behind the schedule. So other questions about billiards? So it'll be one toy model where you'll be able to compute everything if you want to compute it. It's, it won't require, and your intuition is extremely good about it. Now, the way I want to use this toy model is by playing with it and showing, see what are we trying to do. First we looked at individual trajectories, then we looked at little neighborhoods of trajectories, these are Jacobians. Now we want to describe everything. So what are all possible motions? So we want to classify them. For this problem we'll be able to classify them totally. We'll have to produce a complete list of every possible thing that can happen in 3 billiard. That's called partitioning of state space. So every part of state space will have a name. And that you will really understand, you'll be able to do it. However, this is, course in theoretical physics or applied mathematics or whatever nonlinear dynamics is. I have to teach you something that we appreciate in physics very much and not so much in dynamics. So I have to teach you how to use symmetries. And the setting is just right to explain how to use symmetries. So I'll give you a little intuitive picture now, and then we'll do a more serious thing next time. So the simplest billiard we can think of will be the billiard of discs of the same radius. We'll make it 1. Equidistantly spaced, meaning we put them on the centers on the tips of equilateral triangle. So here are 3 discs. And if I connect them, they are an equilateral triangle, and maybe I give them names. Just this is first disc, second disc, third disc. And it's the simplest thing I can do, which is defocusing and has non-trivial behavior. If it was just 2 disks, I would find only one unstable periodic orbit, and there wouldn't be much to describe. So it's very simple repelling thing. But when I have 3 disks, I can go around them anywhere I want. And so that's called chaos. I have infinitely many, exponentially many different, qualitatively different trajectories as I go forward in time. But when I start playing this game, I notice following things. For example, if I find this periodic orbit, so I'll call this orbit, I start at 2, go to 3, and then I go back to 2, go to 3, go forever. So I'll put a bar saying it's an infinite repetition of hitting second and third disk. So that's an example of the simplest possible periodic orbit you can find in a system like that. But the moment I have this one, I also have this one. Now this has different name. I go from 1 to 2 to 1 to 2 to 1 to 2 forever. But you can see that physically they're the same orbit, because this is symmetric. If I flip it, this flips into that. And then there's another orbit here. And that one is called, okay, I'll just continue and you believe anything, right? You're happy?
Oh, you have 1, 3.
Jesus Christ. I'll start teaching English. Okay. So it seems stupid. Why should you compute the same orbit 3 times? So one thing that symmetries do is that once you have computed one element of symmetry set, there are 3 examples of this, then you don't do it again. Here's another example. Suppose I am so clever that I go from here, and then I hit this point, and then hit this point, and I keep going forever. So I'll call this orbit, let me start on 1, then I go to 3, then I go to 2, and I keep repeating it forever. But I can also just reverse the direction of this orbit. So if you wish, I can do time reversal, which is not necessary. So I can decide to start here, go, go, go. And that orbit will be called 1. So I start at 1, I go to 2. From 2 I go to 3 and then go to 1. So I repeat this forever. So it's an orbit that has 3 bounces. So in our first itinerary we'll call a prime orbit, and then the repeats of the prime orbit just goes on forever. But there are 2 of them. Now again, if I just flip this thing, I flip one into the other. So they're symmetry related. So first thing that symmetries do is they relate orbits, but they do something much more amazing, and that I'll just sketch very quickly, and then we'll discuss this at great detail before. You know, if I look at the symmetry axis of this problem, I realize that I'm dividing the system as a pizza into 6 sections. So there's a section like that. And if I flip it, I'll get this section, flip it. So there's 6 identical sections. And what I'll show you is that we can do a beautiful thing. We can just forget all this world of copies, use the grid theory to only look at one piece of pizza. And that will have its, and put mirrors here. Mirror. So the ball will bouncing here, but every ball that bounces here will have a relative in the full space. And it'll turn out it's, if you know this, we know everything, and if you know that, we know this. But this is much, much simpler. So this is really how you use symmetries. And, you do it sometimes in quantum mechanics, the, fundamental cells, etc., when you're quantizing systems, but in classical dynamics works the same way. So I'll do this next time. Any questions?